Now, the first thing I will do is clear out a giant amount of confusion that is rampant on the internet about what exactly precisely spin is. You can see all sorts of nonsense about 4-pi periodic rotations, about, well, spin having something to do with angular momentum to begin with. So let us use this one slide to give a concise summary, without too much mathematical detail, but a concise summary of what precisely spin is and where it comes from. So consider our standard good old Euclidean three-dimensional space in which we live. In that space, we have the usual Euclidean positive definite metric. That's the measure of the distance. And we have our good old angular momentum operators. Those of you who did spectroscopy will remember these lovely expressions and their commutators, which occupied perhaps an entire board full of your lecturers' mathematics when you were doing that in your second year. Now, what these angular momentum operators are is generators of rotations. If you would like to rotate some functions in your three-dimensional space, you say, well, okay, I have a rotation angle, phi, and I have a rotation axis defined by nx, ny, and z, the three components of a unit vector around which we are rotating. Then we put these three operators into this linear combination, we exponentiate it, and the result is a rotation operator in 3 dimensions. And for those of you who did advanced mathematics and group theoretical language, these operators span a Lie algebra that mathematicians called SO3, and then this exponential map goes into the corresponding Lie group of 3-dimensional rotations, and that is our rotation operator. Now, what is important about rotations is that they are a continuous symmetry of physical reality, right? Universe is isotropic. You rotate your experiment a little bit, repeat the experiment, you will see the same result. So it is a continuous symmetry of physical reality. And at that point, Noether's famous theorem turns up and says that every continuous symmetry must lead to a conservation law. And this fact is proven in the theory of Lie algebras. If you ask what is the conservation law that emerges, that is the sum of the squares of all the generators of that group. So Lx squared plus Ly squared plus Lz squared must be conserved. Mathematicians call it Casimir invariant. We call it the total angular momentum, but in any isotropic physical reality, such a quantity will be conserved. And then the usual thing, you remember them all, commutation relations, Lx commutator, Ly is I, Lz, and so on. Usual rotational dynamics. What is important about this is we cannot rotate a point mass in this picture because point mass has an infinite moment of inertia. This is why when you are dealing with linear rotors, you only have rotations perpendicular to the axis but never around the axis in acetylene, for example, because the moment of inertia is too big and the excitations are therefore too high. Okay, but remember, we do not actually live in the Euclidean three-dimensional space. We live in Minkowski space-time, where the metric additionally includes a time-like degree of freedom with a minus in here. And if we look at the corresponding symmetries of space-time, there are extra transformations that pertain to space-time. This is something called Lorentz boosts. Remember the usual picture. When you accelerate an object in a particular direction, it shrinks in that direction and its local time slows down. It is dilated. So that transformation is not a rotation. It's a hyperbolic stretch and squeeze. The object is squeezed, the time is stretched, hence the plus in here. So if you exponentiate this, you get sines and cosines. If you exponentiate this, you get hyperbolic sines and cosines, the usual stretching and squeezing that we remember from special relativity. The interesting thing about these boost operators, and it's also a symmetry group, so-called Lorentz group, is their commutators. If you calculate the commutator of kx and ky, the result is not ikz. The result is ILZ from here. The commutator of two relativistic boosts is a rotation. And so it turns out that in Minkowski space-time there are more ways of rotating things than there had been in Euclidean 3D. In particular, you can now rotate a point mass. If you give it a boost in one direction and then a boost in non-collinear direction, these commutators kick in and the resulting transformation has a rotational component. So in space-time of special relativity, there are more ways of rotating things than we had in Euclidean 3D. The result, of course, is that this Casimir invariant is now modified. In the Lorentz group, we don't just have the 3 generators, Lx, Ly, Lz, we have 6 generators, Lx, Ly, Lz, Kx, Ky, Kz. We must take their sum square under the appropriate metric, so Euclidean metric and the Minkowski metric. This minus gets attached to this case. And so what is conserved in relativistic space-time is this, the sum of L squares, but also subtracted K squares. And this is our usual orbital angular momentum. But the conserved quantity is now modified. We have something else. And let us think about what this conservation law would imply dynamically. So this quantity has to be conserved. If we put this equal to a constant, we will have a bunch of second derivatives here, a bunch of second derivatives there, a bunch of second derivatives here as well. But look, this contains time. So we will have time derivatives. If this is a constant, this gives us an equation of motion. And that turns out, after you work through the mathematics and rearrange it, Wigner did it, that this in fact is what leads to Dirac's equation, out of which, as we know, spin falls out automatically. So the summary of what precisely spin is that there are more ways of rotating things in Minkowski space-time than we had in Euclidean 3D. The fundamental conservation laws that follow from the group theory by Noether's theorem are therefore modified. The correction is called spin. This is where it comes from. Okay, now history. Back to 1896, to the first physical observations that can be traced to the phenomenon of spin. This is Peter Zeemann's paper in 1896 in a Dutch journal whose name I will not even try to pronounce. But what he did is he replaced the previous machine of his that used Bunsen burner with a much higher temperature gas oxygen burner. He took a little bit of asbestos and a little bit of cooking salt, and he just stuffed that into the flame, then put the flame into the magnet, and he reports that the D line of sodium, the famous yellow line, got broader by a factor of 3 to 4. He could not resolve it in his 1896 paper, but an 1897 paper, in fact in the same giant volume of this journal, reports a triplet. So a singlet got split into a triplet when he puts it into the magnet. And of course, these days, this is from the teaching labs. We do it for second-year spectroscopy courses with very, very high-resolution diffractometers these days. This is the red line of cadmium, and it is a singlet when the magnetic field is off, and you can see it splits into a beautiful triplet when the magnetic field is on. Now, Zeeman was rather puzzled by that at the time, and a partial explanation was only worked out by the time quantum mechanics arrived. Remember, of course, in 1896 there wasn't quantum mechanics. So when the orbital theory of Bohr turned up, this became kind of easy to explain, at least for these simple cases. Well, they thought we now have orbital angular momentum. An orbiting charge creates a circular current creates a magnetic moment. Perhaps that thing interacts with the external field. So the orbital Zeeman effect is what was discovered. And from that, of course, Bohr, Sommerfeld, and Debye by then had, from literally just pure combinatorics of integers, have worked out the orbital quantum numbers n, l, and m. And the m came out of these experiments. And if you look at a typical splitting when there is no spin, as we currently know, from 1d2 to 1p1, you will see the actual triplet in here. So partial explanation for the splittings follows from the interaction of orbital angular momentum with the magnetic field. So a singlet splitting was explained by this, but even if you look at the simplest, more complicated case, principal doublet of sodium, you will see that these splitting patterns double up once more. And so this was unexplained at the time. And this was unexplained for 25 years. In 1922, on a stroll through a garden in Göttingen, a particularly downtrodden-looking Wolfgang Pauli was asked, why does he look so unhappy? And he said, well, how can a man look happy when he is thinking about the anomalous Zeeman effect? So even in 1922, this was still unexplained. And of course, I will remind you that Schrödinger only solved his equation for the hydrogen atom in 1926, and even that was spinless at the time. So a partial, decent explanation only arrived in 1926, but by 1922, everybody was still quite puzzled by this. Okay, 1922, Otto Stern and Walter Gerlach. This is a quote from Stern. Referring to Bohr's quantum mechanics in 1913. If this nonsense of Bohr turns out to be correct, we will give up physics. So, of course, what we saw in the previous slide was spectral quantization, and that was the only type of quantization which was known at the time. What people were hunting for is some tangible realization of quantization, something that pertains to something you can poke your finger at, not just a spectrum. And so this was the first observation of spatial quantization of things literally going to different places based on some quantized quantity. And that's the famous plaque from the corresponding department at the University of Frankfurt. If you have a magnetic field gradient, then of course any magnetic dipole is going to move in the gradient. It's insufficient to have just the magnetic field, because the magnetic field would only orient the dipole but not move it. You need a field gradient, and they demonstrated that if you turn that on, something splits. A lot of textbooks claim that this was the discovery of spin. No, it wasn't. They didn't understand what was going on, not for a very long time. This was the discovery of quantization of magnetic moment, right? For reasons at the time uncertain. And of course, they didn't give up physics. Instead, they wrote a very nice postcard to Niels Bohr, congratulating him on the confirmation of the quantum theory. Wir gratulieren zur Bestätigung Ihrer Theorie. And well, you can see these are not really two spots. It's one spot that has been split into something that, you know, can charitably be described as two-valued if you stare at it long enough. Now, there is an apocryphal story about this. Of course, thin films of silver are very nearly transparent. It was not expected, they were not expecting to see anything. What makes silver pitch black and easy to see, as we know, is sulfur or hydrogen sulfide. This is why silver cutlery tarnishes, and you need to, rub it to get rid of it. Silver sulfide is pitch black, really absorbent. And so the apocryphal story went, that goes back to remarks by Stern and Gerlach, that they needed a cigar smoke in the air around the apparatus for these spots to become visible. Not only that, it had to be a particularly bad cigar. And so this was followed up later by Bretislav Friedrich and Dudley Herschbach, who repeated the experiment using a device they have created, and in fact demonstrated that you do need a concentration of hydrogen sulfide in the air for the spots to actually appear. And the bad cigar, of course, refers to the fact that a good cigar wouldn't contain any sulfur to begin with. So it needs to be crappy. And so this is Dudley blowing cigar smoke on a photographic plate to try and get it developed. And they have confirmed that indeed you needed to have been a heavy smoker for that experiment to work. Okay, so that's the cigar story DOI if you're interested in that. Right, so this was the quantization of the magnetic moment. And so that precipitated a little bit of a crisis, because it was unclear in physical terms what the hell was going on. Pauli published a paper that would have never got past the reviewers these days at any journal. So he referred to an intrinsic, classically indescribable kind of dual valuedness of quantum theoretical electrons. So a sign of desperation, if anything. And it was unclear, even in early 1925 to Pauli, what the Zweideutigkeit actually had been. He needed it for the same reason. He needed to introduce, this time, an extra half integer to start explaining the splitting patterns that had to match up between high field and low field. If you go to high field and Zeeman quantization with perturbative, what we now understand, spin-orbit coupling, you do need an extra quantum number. Likewise, for the low field, when we are in the JJ limit, you need an extra half integer to start explaining this. And of course, this completely empirically gave us the Pauli exclusion principle. He realized that closed shells don't have a net magnetic moment, and that multiplet patterns in those splittings, they suggest that one electron orbitals must occur exactly once. This later became known as the Pauli exclusion principle, that no two electrons can have the same four quantum numbers. This, of course, by 1960s turned out to be a super fundamental difference between bosonic and fermionic symmetries of reality, but that was much later. So this famous minus, the Pauli antisymmetry, came from quantum field theory much, much later. So you can see in 1925, this lovely quote in here indicated that there was a bit of a crisis because people understood it partially, but it was still unclear what is causing this remaining splitting. Which brings us to our two heroes, Uhlenbeck and Houtsmit. And Houtsmit is pronounced with an H because he was Dutch. By the time Sommerfeld was recording extremely high resolution hydrogen atom spectra with very, very precise wavelengths accounting. So that's the famous H-alpha line of hydrogen and deuterium containing the simplest case of an unexplained doublet splitting. And here's Uhlenbeck and Houtsmit, both graduate students. One a PhD student, the other just finished his master's. And so they were sent by their supervisor at the time to do the Spektralzoologie, to try and hunt down the missing half integer. And they did find a place for it. Their supervisor, Ehrenfest, characteristically said that this is either nonsense or something very important. So what would a pair of clueless PhD students do if they're asked to explain an inexplicable splitting? Well, of course, they would look around. They would look at the sort of literature that was appearing around the time. Rutherford-Bohr model of the atom was 1913, special relativity 1907, general relativity 1915. Relativistic effects in astronomy were well established at the time. So what the chaps had to do is to cross the road and talk to the astrophysicists, and they probably did. Let's take a look at what was going in astronomy at around the same time. Astronomical bodies, of course, straightforwardly have a mechanical orbital angular momentum and another mechanical angular momentum of their own rotation of the planet, the satellite, whatever it is. That's the usual Newton's second law equations of motion. d momentum by dt is your gravitational potential external force, but then this is the angular momentum of the planet's own rotation around an axis, and in non-relativistic mechanics this is constant because omega is 0, the planet keeps turning. But in special relativity it isn't. There are three terms in here, two of which were known at the time that we are now considering. Lense-Turing effect, look, this is orbital angular momentum of the planet around the Sun talking to its own orbital motion. This is the astronomical coupling between the orbital angular momentum and the planet's own rotation. Nothing to do with quantum mechanics, purely mechanical relativistic. There is also the coupling between two rotational motions of spinning bodies, and Thomas precession was discovered much later. So it is the kinematic wobble of the axis of rotation if you are close to relativity. Lense-Turing effect, so if the planet is spinning and you are orbiting it, your orbit lines will not connect. And this spin-spin coupling is only relevant in black hole collisions, so not really on any reasonable energy scale here on Earth. But look at this. Orbital angular momentum interacts with the spinning of the planet. But of course, these are all gravitational effects. So what they did was to try and do something similar. They said, well, okay, let's stick some kind of spin-orbit coupling. Let's assume that maybe the electrons turning around its axis turned out to be incorrect, as we shall see, but that was the inspiration. So we put the orbital angular momentum, we put something else, maybe some kind of intrinsic angular momentum, we stick a coefficient in front, and we hope for the best. This is how physics is done, even this day. Of course, you instantly get the splitting that was missing in there, but only when this quantity has exactly two observable values. So the corresponding operator in quantum mechanics must have exactly two eigenvalues. And they published it in 1926, and Ehrenfest submitted it to the journal before they could reconsider, because they later realized that all sorts of things were potentially wrong with that explanation. Pauli pointed out that it's not actually possible for a multiplicative or integra differential operator to have exactly two eigenvalues. You either have none or you have infinitely many. There is no way you can have exactly two. Lorentz estimated the speed, the surface velocity that a classical electron at a classical radius would require to produce that kind of orbital motion, 10 times the speed of light. And then, of course, Wigner and company, who understood group theory, pointed out that SO3 doesn't even have two-dimensional irreducible representations. All irreps of rotation group are odd-dimensional, 1, 3, 5, SPD, F, and so on orbitals. And if you try and talk the SO3 to have two-dimensional irreps, you get non-physical interpretations like 4-pi periodic rotations, which are obviously nonsense in three-dimensional space. This is not a deep physical fact. This is reductio ad absurdum. If you try and force that to be rotational motion, you get unphysical kinds of rotations. Heisenberg sent a nice letter to these two, calling their paper Seine mutige Note, your brave note, and asked them politely how did they get rid of the factor of 2, and what they realized immediately is that they have lost a multiplicative factor of 2. So if you put all the numbers in, they're a factor of 2 off from what the experimental splitting was supposed to have had. And so, well, Uhlenbeck in his memoirs says, I must say Sam and I had not really appreciated this basic difficulty. So a pair of PhD students just hacked something together, which literally explained everything immediately without any clear explanation of what the hell this is. So mathematically, everything worked. Physically, it was still utterly unclear what was going on. This period, late 1925 to 26, is best called the Great Confusion. This is a letter from Llewellyn Thomas, a Scottish physicist, to Sam Houdsmith. The usual pleasantries here. I think you and Uhlenbeck have been very lucky to get your spinning electron published and talked about before Pauli heard of it. It appears that more than a year ago, Kronig believed in the spinning electron and worked out something. The first person he showed it to was Pauli. Pauli ridiculed the whole thing so much that the first person became also the last, and no one else heard anything of it, which all goes to show that the infallibility of the deity, meaning Pauli, does not extend to his self-styled vicar on Earth. Kronig had the explanation, he talked to Pauli, Pauli talked him out of it, he never published anything on the subject. Don't listen to your supervisors. Lorentz, that is very difficult because it causes the self-interaction energy of the electron to be wrong. Ehrenfest, well, that's a nice idea, it can be wrong, but you don't yet have a reputation, so you have nothing to lose. He was their direct supervisor. Bohr, on your way home you should stop off at Hamburg and explain the lost factor of 2 to Pauli. They didn't know. Pauli, Eine neue Kopenhagener Irrlehre, the new Copenhagen heresy. The previous Copenhagen heresy was, of course, the Copenhagen interpretation. So Pauli didn't mince words. He hated the entire idea. It took some time for him to be convinced. And so it was actually Llewellyn-Thomas that found that factor of 2, but everyone was intensely uncomfortable with that situation. Okay, the factor of 2. What do you do if you've lost a factor of 2 in your research? Well, you just honestly admit it in your paper. So if you read this 17th of October 1925 paper, by the two of them, the value of the magnetic moment is different, doppelt so groß sein, as für die Umlaufsbewegung. So they've actually admitted that they have it, and they have no explanation for that. Thomas revisited the frame transformation. So, of course, what the two had assumed in their mathematics is that they do this transformation into the instantaneous frame that is connected with the electron, and then there's an extra magnetic moment that's turning up, and that's their splitting. Llewellyn-Thomas pointed out that, of course, the frame of reference centered on the electron is non-inertial because it's a curvilinear motion. So you have to have the non-inertial corrections in the special relativity. And once he worked through those corrections, the factor of 2 magically popped out and everything was correct. At that point, Pauli immediately became convinced because the mathematics has worked out, and everybody suddenly became at peace with this explanation because it all fitted in, and there were good physical reasons for why it should have fitted in. So introducing special relativity into that picture solved it. And then 50 years ago, exactly 50 years ago, there are 2 autobiographical papers by Uhlenbeck and Hautsmith separately, and you can sort of see it in the title, the uncertainty that reigned it, that even 50 years later, they finally maybe just about reconciled themselves to that it might as well be spin. Right, so it was a traumatic experience, I think, for the physics community at the time. And I encourage you to download the Sonderdruck aus den Naturwissenschaften paper. That is what we are celebrating at the moment. Okay, so the actual correct proper explanations and later turned out from Dirac and Wigner, and in a very strange way from Dirac, because Dirac pretty much also guessed his equation. What he did is he just hacked the relativistic energy momentum relation. So this is what we get from special relativity, and Dirac said, well, let's just stupidly try to quantize it in the usual way by replacing the energy with the Hamiltonian and momentum with the corresponding operator. But of course, this is the Hamiltonian square. You need the original Hamiltonian. And then he said, well, okay, let's assume it's multilinear in mc squared and the 3 momenta, and let's find the coefficients such that this squares into that. He realized that such coefficients do not exist. And by some stroke of genius, he realized that if these are matrices and the smallest dimensions 4 by 4, then you can find such matrices. And so that, of course, then turned out to be Pauli matrices. But for Dirac, this was a dubious hack, as he admits in his biography, and the colleagues have called it Dirac's coup. The rigorous derivation was supplied by Eugen Wigner some time later. He started with basic symmetries and Noether's theorem. He used group theory to get that Casimir invariant of the Lorentz group, and he got the equation of motion, which turned out to be Dirac's equation. Now, this is getting mathematically too complicated for this lecture. Let me just give you one slide that illustrates the Wignerian thinking on the subject, and this is how much of modern theoretical physics operates. We start with basic symmetries of physical reality, and we take them into the framework equations for how that reality can evolve. So that's Wigner's type of logic. Let's assume that physical reality, first of all, this is important, is knowable, philosophically knowable, which implies that for any finite and isolated physical system, there is a possibility of describing it. So some kind of descriptor must exist, not necessarily a wave function, but a descriptor of some kind. We will also assume that reality has rules. We don't know what they are, but we assume that they exist. And those rules will be taking us forward in time. If we have the state descriptor at time t, the rules of evolution will take us to time t plus t prime, and the operator that applies the rules, it's called a propagator. We don't know what it is, but we assume that it exists. The rules, if we look at them, appear to be the same today as they had been tomorrow. So this propagator cannot depend on absolute t and t prime. It can only depend on their difference, right? How much time has passed. And so this is then tau, and so our descriptor at t plus tau will be our descriptor at t and the propagator through tau. But then, of course, for every propagator, there must be a unique inverse. There should be a unit propagator for tau equals 0 that does nothing, and superposition of two propagators is another propagator. That's called a Lie group. So suddenly we have a group theoretical structure there. Reality also looks continuous, and velocities are aspects of that reality, so every derivative must exist. As soon as all derivatives exist, we can use a Taylor series. Let's do that. Psi of t plus tau, Taylor expansion in tau. Look at this. Tau to the n, d by dt to the n factorial. This is the exponential of a time derivative with the tau. And matrix exponentials are allowed, operator exponentials are allowed because differentiation is assumed to exist. But this is Lie theoretical structure. This is the exponential map from an algebra. So the time evolution generator is in fact d by dt. So, well, let's find out what it might be. From group theory, we know that Lie groups allow unitary irreducible representations. This is a uniparametric and therefore abelian Lie group. The irreps must be one-dimensional. And actually, from basic calculus, we know what they are because we know the eigenfunctions of d by dt. They are complex exponentials with some frequency. We can always choose them this way from mathematical considerations. And so it turns out that for each irrep, the action by d by dt is represented by a multiplication by this number. But an arbitrary representation of a Lie group is a direct sum of irreducible ones. So an arbitrary representation must be a diagonal matrix minus I bunch of real numbers here. But any group representation is defined up to a similarity transformation. If we do a similarity transformation on this, we get a Hermitian matrix. And so d by dt is minus IH. You can recognize a Schrödinger type equation. Without the wave function, you can multiply, of course, the descriptor in, but fundamentally it's an operator relation. And look at what we had here. We only assumed that reality is knowable, continuous, and has unchanging rules, and we suddenly got the framework equation of motion for it. This is the kind of logic that if you then apply it to translational degrees of freedom, rotational degrees of freedom, and boosts, eventually gets you the Dirac's equation. Right? You need to know group theory in order to be able to derive such things. Okay, so the summary of mathematics, our eyes convince us that physical reality is causal, continuous, uniform, and isotropic. Causality and continuity give us Schrödinger-like equations of motion. Uniformity, I have skipped that slide, but it gives us the energy-momentum relation. The fact that it's isotropic and Lorentz invariant, and we know that from Michelson-Morley's experiment, after an exercise in group theory gives us this Casimir invariant, and what it needs to be equal to comes from the experiment, from that hydrogen splitting. All of this together, once you work through the mathematics, gives you Dirac's equation, which has positive and negative energies corresponding to matter and antimatter, or rather the surface of the Dirac sea from which you can get matter and antimatter. After you go into, believe it or not, the same rotating frame transformations that we use in magnetic resonance to eliminate the large Zeeman energy gaps. In this case, the energy gap is about a mega electron volt. It's an electron-positron energy gap. But after you work through it to first order, in the average Hamiltonian theory, you get Zeeman interaction with the magnetic field, and this is a spin operator now. And if you work through the second order, you also get the spin-orbit coupling, the relativistic mass correction, and the Darwin term for the electron. And so, essentially, skipping all of the complexity here, you will find it in the better textbooks. The story is that in relativistic space-time, there are more ways of rotating things than we had in R3. The conservation law is modified, and the correction is spin. So it makes an appearance because time is a degree of freedom in special relativity. And so to finish, let's take a look at what this has all led to. over the last 100 years. Of course, Lorentz and Zeeman got the Nobel Prize for the work. You can see that the people who award the Nobel Prize are Swedish. They are researchers into the influence of magnetism upon radiation phenomena. Otto Stern got it, and that's a story there. Gerlach didn't get it. The reasons were nakedly political. In October 1943, Otto Stern got the Nobel Prize. 2 months later, on the 2nd of December 1943, Walter Gerlach accepted the job as one of the heads of the German nuclear weapons program. As we know, he has very nearly succeeded, which all goes to show that we should be careful who we piss off in the academic system, right? Maybe if he did get the Nobel Prize, he would not have turned that kind of nasty. Isidor Rabi, of course, electron, nuclear magnetic resonance, magnetic properties of atomic nuclei in 1944. Purcell and Bloch for what we now know as nuclear magnetic resonance. Kusch for the correction to the G factor, the quantum field theory correction to the G factor of the electron. Of course, Richard Ernst and Kurt Wüttrich, 2 separate Nobel Prizes separated by 10 years, but they're essentially indistinguishable. This is our modern magnetic resonance spectroscopy as we know it. The 2 Muppets didn't get their Nobel Prize for obvious reasons, I think. And of course, magnetic resonance imaging very recently, Lauterbur and Mansfield. So I am trying to pull as many good magnetic resonance papers into Science Advances as I can. Let me show you what was published over the last couple of years in there. You can now have magnetic resonance pulses that selectively excite chemically exchanging signals. So if there is no chemical exchange, it wouldn't appear. If there is an exchange, the signal will turn up. Quite how you even do it was a puzzle to me until I read that paper, so go ahead and read it. So this is one of the foundational discoveries last year in our entire business. New instruments are coming up. Alex Barnes and company. Magic angle spinning spheres, spherical rotors in solid-state magnetic resonance. This came out last month. Pravdivtsev group has found a way to slow down relaxation by adding a chemical. It used to be easy to accelerate it. You just put some chromium acetylacetonate in there and the relaxation accelerates. But how on earth do you slow down nuclear relaxation by adding things? Well, read the paper. Burkhard, Louis and company, this is a very hot topic in modern magnetic resonance, quantum optimal control. Better sensitivity, faster experiments, more precise magnetization transfer. Rick group, super resolution, triple resonance, NMR spectroscopy. We all know where the ultra-fast magnetic resonance started from, so that is a variation on the same topic. Something we just sent there, chemical hydrodynamics of nuclear spin states. How do you deal with spin processes in the simultaneous presence of chemical kinetics, hydrodynamics, diffusion, and flow? And the very recent paper from Kaminker group, Nurit, Fred, and Ilya are both formerly of our parish here at Weizmann Institute. So now this is Tel Aviv University, and they just published an instrument that can do simultaneously NMR, EPR, DNP, and magic angle spinning. So these are extraordinary developments that are ongoing. So we just commissioned a 12-review special issue titled 100 Years of Spin. Lucio's writing the part on magnetic resonance, and it goes from neutron stars, all the way to spintronics and magnetic data storage, magnet engineering and so on. When that comes out, do take a look. We asked everybody who has anything to do with spin in the world to write a review of their area in there. And that's me. Thank you for your attention.